Hello, my name is Jeremy Comel, and today I'm going to be talking about redox lipidomics, the study of oxidized lipids. Oxidative damage is a universal indicator of stress, both mental stressors and exposures, for example, to toxic chemicals, high-fat diet or other unhealthy diets, drugs, or numerous disease states can all lead to free radicals. These free radicals in turn can cause oxidative damage, especially to lipids, which are prone to oxidative damage due to their allylic hydrogens. Therefore, it is essential to understand oxidized lipids and be able to detect them in order to determine early on onsets of disease, stress markers, figure out what the toxic effects of these oxidative products are. They're also served as signaling molecules. And so we've applied the software we've developed in a number of applications, including alcoholic liver disease, where we find that oxidized triglycerides are early indicators of disease in liver, even before histological changes can be observed. We found it in environmental applications, for example, seagrasses and other plants with phosphate deplete conditions show oxidized stress and oxidized lipids. We found them in fish in South Africa with an inflammatory disease called pancreatitis compared to healthy controls, etc., etc. So oxidized lipids do seem to occur, as we would imagine, as universal indicators of stress. We've developed LipidMatch oxidized libraries to be as comprehensive as possible while still being functional. So we have 6 different types of oxidations. We include 2 short chain, aldehyde and carboxylic acid termini, and 4 long chain, which are inserted along the fatty acid chain, including epoxy, ketone, hydroxy, and hydroperoxy. We also include multiple additions of oxidations, not just single oxidations. So for example, for long chain products, for 18-2, for a single oxygen it would be a hydroxy. But then for 2 oxygens or more, you can have multiple isomers. So for example, they might have 2 hydroxy or 1 hydroperoxy, but the fatty acid would still have the same molecular formula and hence mass. In fragmentation, we often can't discern these because the fragmentation happens at the ester linkage of the lipid, and so we only get the total fatty acid mass as the most abundant fragment, and therefore we can't distinguish between these different types of oxidations with the same number of oxygen additions. These oxidized fatty acids are then combined with natural fatty acids, unoxidized fatty acids, and different types of lipids, including glycerolipids, cardiolipids, and phospholipids and lysophospholipids, to give a diverse library covering many different types of oxidized species that may be observed. An interesting note, just like we can't tell the isomers of different types of oxidations necessarily using traditional MSMS approaches and LipidMatch software, we also can't tell the position of oxidation on the fatty acid chain. For example, here you can see how different oxidations could occur at 3 different possible positions given 2 double bonds. Taking 18:2 with different types of positions of the oxidations and different types of oxidations and different numbers of oxidations, you can actually get 108 total oxidized species just for this single fatty acid. Note that that would mean that you could get over 1 million oxidized triglycerides just thinking about 18:2. If you think about all the possible fatty acids, you can actually get over 1 billion oxidized triglycerides. While LipidMatch libraries only contain tens to hundreds of thousands of these oxidized species, we still are able to observe quite a large diversity within real experiments. So for example, we did an oven versus pan frying with Mira's lab, and we compared oxidized lipids in soy, walnut, and olive oil using these 2 different cooking techniques. We were able to identify over 3,000 oxidized triglycerides, although not all of these were separated by chromatography, although they were separated by MSMS fragmentation. We then wanted to see how confident our identifications were of these oxidized lipids. Comparing these oxidations that we observed using LipidMatch to traditional assays, we see very similar trends across unheated, oven-fried, and deep-fried soy, olive, and walnut oil, as you can see in these left and right panels. In the left panels are chemical assays, conjugated diene values, for example. When you get an addition of an oxygen, no longer are those double bonds separated by a carbon. Now they're right next to each other, which is conjugated double bonds, and you can observe this difference using spectrometry, spectroscopy. And so here you can see that on the left you get these traditional assays, and on the right we summed up the intensities of those annotated lipids that had two double bonds and a single or more oxidations. And you can see that indeed the patterns that we observe, the trends, are identical, showing that we are showing the same results as traditional assays. Same thing for the conjugated triene values, and then I am not showing it here, but the acid values were similar with some differences, and the aldehyde values were very similar as well, the trends we observed. And so that summarizes the talk. I'd like to note here that we provide free software which increases molecular MSMS and annotation coverage at innovativeomics.com. Quite a diverse range of software for lipidomics and environmental analyses. And oxidized lipids are sensitive markers of disease and environmental stress we've shown in many applications, and we need to know more. Now there are tools out there, including LipidMatch, and we need more researchers to start to apply them to their applications. Thank you.